So basics of X-ray we discuss. So basically X-rays were discovered by Rontgen in 1895, very long back, and accidentally he has discovered these X-rays, and it is named as X-rays because they are not given a name at that particular time, and same name was uh, continued. Okay, X means it is a unknown. So X is representing unknown. It is a unknown ray, electromagnetic radiation, and it was named by Rontgen at that particular time, and same name was continued nowadays also. So these X-rays are basically electromagnetic radiations. They are electromagnetic waves of short wavelengths. The wavelength of X-rays are very short compared to the visible region, and they are having the wavelength in the range of 10 angstrom to 0.5 angstrom. Okay, usually they have the wavelengths ranging from 10 angstrom to 1 angstrom. Okay, very small range of wavelength is observed for X-rays. The longer wavelength end of the spectrum is known as soft X-rays. Okay, longer wavelength, that is 10 angstrom, 9 angstrom, that region is called as the soft X-rays, and shorter wavelength X-rays are called as hard X-rays because they are having higher energy. Because the lower wavelength radiations have high energy because they will have higher frequency, and that will represent the hard X-ray. Soft X-rays are the longer wavelength X-rays. The shorter wavelength X-rays are called as hard X-rays. Okay. Then X-rays are produced when fast-moving electrons are suddenly stopped by the solid target. So when X-rays are produced when fast-moving electrons are suddenly stopped by the solid target. Then those electrons will be absorbed by the target, and that will produce X-rays. Okay, and usually the Coolidge tube is used to produce X-ray. Okay, the method of producing the X-ray is done by the Coolidge tube. This is the Coolidge tube. It contains a high tension battery connected to the two ends. Then there is a cathode. Okay, that cathode produces fast moving electrons. That fast moving electrons will collide with this particular target, and this target is maintained at positive potential. Because of that, electrons will attract towards this target. When these electrons are suddenly stopped, then that energy will be converted into electromagnetic radiation, and it is observed that these electromagnetic radiations are in the range of the wavelength of X-rays. Okay, that is a very simple thing or simple technique to produce the X-rays. Here, the frequency of X-rays emitted using the Coolidge tube depends on the voltage between the cathode and anode, because the voltage between the cathode and anode decides the speed of the electron. If the voltage is more, the speed of the electron will be more. If high speed electron hits the target, higher energy X-rays are produced. That means higher frequency X-rays are produced. That is simple thing. Let us take V is the accelerating potential across the tube, and E is the charge of the electron. Then work done on the electron in moving from the cathode to anti-cathode or cathode to anode is equal to charge into potential. Okay, E into V, that is the energy of electron which is moving from cathode to anode. This energy will be converted into electromagnetic radiation. The electron thus acquires kinetic energy, which is converted into X-rays. Okay. The electron thus acquires kinetic energy, and that kinetic energy will be converted into X-rays when the electron strikes the target. So when high speed electron strikes the target, that will produce the X-rays, and here the energy of the electron will be converted into the electromagnetic radiation. If entire amount of kinetic energy of electron is converted into X-ray, then you can find out the maximum frequency of the X-ray produced is given by H nu max equal to E into V. So H nu max represents the highest energy of the X-ray produced. If entire energy of the electron is converted to X-ray without any energy loss, then maximum energy produced equal to H nu max, where nu max is the maximum frequency of the X-ray produced. If entire kinetic energy of the electron is converted into the electromagnetic radiation, that is X-ray. If h nu max equal to E into V, you can find out the minimum wavelength. Minimum wavelength of the X-ray produced, that is given by lambda minimum is equal to C by nu max, which is equal to Hc by Ev. If you substitute for nu max, that is equal to Ev by H. So nu max equal to Ev by H. You will get the minimum wavelength of the X-ray produced, lambda minimum equal to Hc by Ev. Okay, where V is the potential applied, E is the charge of the electron, H is Planck's constant, C is velocity of electromagnetic radiation. It is velocity of light only. Okay, so both things you have to remember. The maximum frequency of the X-ray produced by Coolidge tube is given by h nu max equal to Ev. The minimum wavelength of the X-ray produced is lambda minimum equal to Hc by Ev. Okay, these two formula you have to remember corresponding to the production of X-ray. Okay, next we will try to complete this Bragg's law also. So basically Bragg's law is defined using the diffraction of X-rays because of the crystal planes. When monochromatic X-ray impinge upon the atoms in the crystal lattice, each atom acts like a source of scattering of radiation of the same wavelength. Okay, so these X-rays are going to be scattered by the crystal planes, and these crystal planes are observed to produce a diffraction. Basically, the wavelength of X-ray is equivalent to the lattice constant of the crystal. Lattice constant of the crystals are also in the range of angstroms, and the wavelength of the X-ray is also in the range of angstrom. Therefore, the diffraction of X-ray can be observed. So this scattering of X-rays is equivalent to the diffraction of X-ray in this particular case. The crystal acts as a series of parallel reflecting planes. Okay, so here diffraction is taking place because of the reflection, and these crystals having this series of sets of atoms, and they are in the form of planes. They are acting like a parallel reflecting planes. I will show you in detail. And the intensity of the reflected beam at a certain angles will be maximum when the path difference between the two reflected waves from two different planes is an integral multiple of lambda. That is the condition for diffraction. If path difference between two rays is equal to the integral multiple of the wavelength, then you can find the maximum intensity, and that is called as diffraction maximum. Okay, so that the diffraction maxima is observed for a particular angle of incidence. Let us take this particular case, that is derivation of Bragg's law. Consider a set of parallel planes of atomic points at a spacing d between two successive planes. Let us take the two planes are separated by d, and these two planes are consisting of atomic points, and the rays narrow monochromatic X-ray beam of wavelength lambda be incident on the first plane at the glancing angle theta. Suppose X-rays are incident on this plane at an angle of theta. Remember, it is not the angle of incidence, it is called as glancing angle. Glancing angle is defined as the angle between the incident ray with respect to the parallel planes. Okay, so it is angle between this incident ray with respect to the incident plane, not with respect to normal. Remember this. So glancing angle is theta. Now consider the ray PQ, which is incident on the first plane. PQ is incident on the first plane, and it is reflected along QR, and again it makes an angle of theta with respect to the plane here. Consider two parallel rays, another parallel ray P dash Q dash, which is parallel to PQ, which is going to pass through the first plane and it incident on the second plane. Okay, so and it is reflected along Q dash R dash. Okay, two rays are going to be reflected, and these two rays are making an angle of theta with respect to these parallel planes, and these planes are separated by D. Now Q dash is vertically below Q. We have arranged such that Q dash is exactly below the Q. Now the ray P dash Q dash R dash is traveling longer. Its path is longer compared to this PQR. Therefore, there is a perfect path difference between them. Okay, it travels shorter distance, whereas this P dash Q dash R dash travels longer distance. You have to find the path difference between these two. So for that, what you will do, we'll take the normals to this P dash Q dash. That normal is QT, and normal to Q dash R dash is QS. We'll draw a normal. Now this P dash T is exactly equal to PQ because this is perpendicular. The distance traveled by PQ is exactly equal to distance traveled from P dash to T. Similarly, the distance traveled by the ray from Q to R is exactly equal to S to R dash. So this is the basically the extra path traveled by the secondary. Okay, because PQ is equal to P dash T, SR dash equal to QR. This TQ dash plus Q dash S is the extra path difference. Therefore, the path difference between these two rays is equal to TQ dash plus Q dash S. And according to trigonometry, this is angle theta. The angle between Q dash is theta. Therefore, sin theta is given by this adjacent by sin theta is given by opposite by hypotenuse. So hypotenuse is Q dash, it is D. TQ dash is opposite. Therefore, TQ dash is given by D sin theta. Similarly, so here this TQ dash is equal to D sin theta, and Q dash S is also equal to D sin theta. That is equal to 2D sin theta. Okay. So this is the path difference. So total path difference between these two rays is equal to 2D sin theta. Okay, 2D sin theta is the total path difference between these two rays. And according to the diffraction maxima, concept of diffraction, the two rays produce diffraction maxima if a path difference is integral multiple of lambda. Okay, the two rays produce diffraction maxima if path difference is integral multiple of lambda. Therefore, this path difference 2D sin theta must be equal to n lambda, where lambda is the wavelength of incident X-ray. So this particular expression is called as Bragg's law of X-ray diffraction, or it is sometimes called as X-ray reflection also. So here this n can take the integer values 1, 2, 3, etc. The integer n gives the order of the scattered beam, and lambda is the wavelength of X-ray used. And this equation is called as Bragg's law. It is very, very important. It is used to find out the interplanar distance. That is distance between one crystal plane to next crystal plane. Basically, this Bragg's law is used to find out the distance between one plane to next plane. By knowing the angle of, that is glancing angle between this incident ray and the crystal plane, you can find the value of D if you know the value of lambda. So X-ray wavelength, if you know the angle of glancing, then definitely to find out the distance between the planes. So that this Bragg's law is basically used to find out the distance between the crystal planes. Okay, so from one lattice point to next lattice point, otherwise one atom to next atom, what is the distance? Basically, the distance between the atoms can be found using this study of the X-ray diffraction. Okay, the concept is very clear. The wavelength of X-ray is comparable to the distance between the atoms. So diffraction is observed if the obstacle is comparable to wavelength of the radiation used. And here, these atoms act like an obstacle. These atoms are acting like obstacles. Therefore, the distance between the atoms is comparable to the wavelength of X-rays. So first you have to find the path difference. It is very simple. So path difference is D sin theta plus D sin theta, that is equal to 2D sin theta. and that path difference must be equal to integral multiple of lambda. Okay, so that gives you the expression of Bragg's law. So Bragg's law is given by 2d sin theta equal to n lambda, where d is the distance between crystal planes or distance between the atoms. Theta is the glancing angle of the incident X-ray. N is integer, it can take 1, 2, 3, etc. First order diffraction, second order diffraction, like that. Lambda is the wavelength of X-ray used. Okay, so that is about Bragg's law. So Bragg's law gives the relation between the interplanar distance and the wavelength of X-ray used. Okay, so remember, D is called as interplanar distance. Interplanar distance means it is the distance between two consecutive crystal planes, two consecutive parallel crystal planes. That is called as interplanar distance. And in the next class, we will take up the concept of interplanar distance, derivation of interplanar distance we will consider in the next class. We will try to express this interplanar distance D in terms of HKL. Okay, that is Miller indices.